Dividing line between the two halves of the pattern. Bottom board. This is a board which is normally made of wood and is used at the start of the mold Mac ing. The pattern is first kept on the bottom board, sand is sprinkled on it, and then the ramming is done. Design patterns and cores for metal casting process. Understand the various molding materials used in the making of molds and cores. 3.1 Introduction. Casting is one of the earliest metal shaping methods known to human being. It generally means pouring molten metal into a refractory mold with a cavity of the shape to be made and allow it to solidify. When solidified, the desired metal object is taken out from the refractory mold either by breaking the mold or taking the mold apart. The solidified object is called casting. This process is also called founding. 3. That iron casting technology in India has been in 3.1.2 Advantages and limitations. Casting process is extensively used in manufacturing because of its many advantages. Molten material flows into any small SEC tie-in in the mold cavity, and as such any intricate shapes, internal or external, can be made with the casting process. It is possible to cast practically any material, be it ferrous or non-ferrous. Further, the necessary tools required for casting molds are very simple and inexpensive. As a result, for trial product tie-in or production of a small lot, it is an ideal method. It is possible in casting process to place the amount of material where exactly required. As a result, weight reduct tie-in in design can be achieved. Castings are generally cooled uniformly from all sides, and therefore they are expected to have no directional properties. There are certain metals and alloys which can only be processed by the casting, and not by any other process. Like forging because of the metallurgical considerations. Casting of any size and weight, even up to 200 tons, can be made. However, the dimensional accuracy and surface finish achieved by normal sand casting process would not be adequate for final application in many cases. To take these cases into consider a tie-in, some special casting processes such as die casting have been developed, which are discussed in later chapters. Also, the sand casting process is labor-intensive to some extent, and therefore many improvements are aimed at it like machine molding and foundry mechanization. With some materials it is often difficult to remove defects arising out of the moisture present in sand castings. 3.1.3 Applications. Typical applications of sand casting process are cylinder blocks, liners, machine tool beds, pistons, piston rings, mill rolls, wheels, housings, water supply pipes and specials, and bells. 3.1.4 Casting terms. In the following chapters, the details of sand casting which represents the basic process of casting would be seen. Before going into the details of the process, defining a number of casting vocabulary words would be appropriate. Reference may please be made to Fig. 3.1. Flask. A molding flask is one which holds the sand mold intact. Depending upon the position of the flask in the mold structure, it is referred to by various names such as drag, cope and cheek. It is made up of wood for temporary applications, or more general LLY of metal for long-term use. Metal casting processes. 3.3. Ladle. Sprue. Parting line. Runner mold cavity core drag. Cope. Riser. Pouring basin. Vent. Fig. 3.1 Cross-section of a sand mold ready for pouring. Drag lower molding flask. Cope upper molding flask. Cheek intermediate molding flask used in three-piece molding. Pattern is a replica of the final object to be made with some modifications. The mold cavity is made with the help of the pattern. Parting line. This is the dividing line between the two molding flasks that makes up the sand mold. In split pattern it is also the dividing line between the two halves of the pattern. Bottom board. This is a board which is normally made of wood and is used at the start of the mold Mac ing. The pattern is first kept on the bottom board, sand is sprinkled on it, and then the ramming is done in the drag. Facing sand, the small amount of carbonaceous material sprinkled on the inner surface of the mold ing cavity to give better surface finish to the castings. Molding sand. It is the freshly prepared refractory material used for making the mold cavity. It is a mixture of silica, clay and moisture in appropriate proportions to get the desired results, and it surrounds the pattern while making the mold. Backing sand. It is what constitutes most of the refractory material found in the mold. This is made up of used and burnt sand. Core. It is used for making hollow cavities in castings. Pouring basin. A small funnel-shaped cavity at the top of the mold into which the molten metal is poured. 3.4 Manufacturing technology, foundry, forming and welding. Sprue. The passage through which the molten metal from the pouring basin reaches the mold cavity. In many cases it controls the flow of metal into the mold. Runner. The passageways in the parting plane through which molten metal flow is regulated before they reach the mold cavity. Gate. The actual entry point through which molten metal enters mold cavity. Chaplet. Chaplets are used to support cores inside the mold cavity to take care of its own weight and overcome the metallostatic forces. Chills are metallic objects which are placed in the mold to increase the cooling rate of castings to provide uniform or desired cooling rate. Riser. It is a reservoir of molten metal provided in the casting so that hot metal can flow back into the mold cavity when there is a reduction in volume of metal due to solidify CA tie-in. 3.1.5 Sand mold making procedure. The procedure for making a typical sand mold is described in the following steps. First, a bottom board is placed either on the molding platform or on the floor, making the surface even. The drag molding flask is kept upside down on the bottom board along with the drag part of the pattern at the center of the flask on the board. First, a bottom board is placed either on the molding platform or on the floor, making the surface even. The drag molding flask is kept upside down on the bottom board along with the drag part of the pattern at the center of the flask on the board. There should be enough clearance between the pattern and the walls of the flask, which should be of the order of 50 to 100 millimeters. Dry-facing sand is sprinkled over the board and pattern to provide a non-sticky layer. Freshly prepared molding sand of requisite quality is now poured into the drag and on the pattern to a thickness of 30 to 50 millimeters. Rest of the drag flask is completely filled with the backup sand and uniformly rammed to compact the sand. The ramming of the sand should be done properly, neither to compact it too hard, which makes the escape of gases difficult, nor too loose, so that mold would not have enough strength. After the ramming is over, the excess sand in the flask is completely scrapped using a flat bar to the level of the flask edges. Now, with a vent wire, which is a wire of 1 to 2 millimeters diameter, with a pointed end, vent holes are made in the drag to the full depth of the flask as well as to the pattern to facilitate the removal of gases during casting solidification. This completes the prep tie-in of the drag. The finished drag flask is now rolled over to the bottom board exposing the pattern as shown in Fig. 3.2c. Using a slick, the edges of sand around the pattern is repaired and cope half of the pat turn is placed over the drag pattern, aligning it with the help of dowel pins. The cope flask on top of the drag is located aligning again with the help of the pins. The dry parting sand is sprinkled all over the drag and on the pattern. A sprue pin for making the sprue passage is located at a small distance of about 50 millimeters from the pattern. Also a riser pin, if required, is kept at an appropriate place and freshly prepared molding sand similar to that of the drag along with the backing sand is sprinkled. The sand is thoroughly rammed, excess sand scraped. And vent holes are made all over in the cope as in the drag. The sprue pin and the riser pin are carefully withdrawn from the flask. Later the pouring basin is cut near the top of the sprue. The cope is separated from the drag and any loose sand on the cope and drag interface of the drag is blown off with the help of bellows. Now the cope and the drag pattern halves are withdrawn by using the draw spikes and wrapping the pattern all around to slightly enlarge the mold cavity so that the mold walls are not spoiled by the withdrawing pattern. The runners and the gates are cut in the mold carefully. Metal casting processes 3.5. Without spoiling the mold. Any excess or loose sand found in the runners and mold cavity is blown away using the bellows. Now the facing sand in the form of a paste is applied all over the mold cavity and the runners, which would give the finished casting a good surface finish. A dry sand core is prepared using a core box. After suitable baking, it is placed in the mold cavity as shown in Fig. 3.2. The cope is replaced on the drag taking care of the alignment of the two by means of the pins. A suitable weight is kept on the cope to take care of the upward metallostatic force during the pouring of molten metal. The mold now, as shown in Fig. 3.2e, is ready for pouring. 3.2 patterns. As has been defined earlier, a pattern is a replica of the object to be made by the casting process, with some modifications. The main modifications are: A. Drag completed. B. Ready for rollover. C. After rollover. D. Cope rammed. E. Mold ready for pouring. Cope. Drag. Weight. Fig. 3.2 Sand mold making procedure. 3.6 Manufacturing technology, foundry, forming and welding. A. The addition of pattern allowances. B. The provision of core prints. And C. Elimination of fine details which cannot be obtained by casting and hence are to be obtained by further processing. 3.2.1 Pattern allowances. The dimensions of the pattern are different from the final dimensions of the casting required. This is required because of the various reasons. These are detailed as follows. Shrinkage. All the metals shrink when cooling except perhaps bismuth. This is because of inter-atomic vibrations which are amplified by an increase in temperature. However, there is a distinction to be made between liquid shrinkage and solid shrinkage. Liquid shrinkage refers to the reduction in volume when the metal changes from liquid to solid state at the solidus temperature. To account for this, risers are provided in the molds as explained in Chapter 4. Solid shrinkage is the reduction in volume caused when metal loses temperature in solid state. The shrinkage allowance is provided to take care of this reduction. The rate of contraction with temperature is dependent on the material. For example, steel contracts to a higher degree compared to aluminium. The shrinkage also depends upon the metallurgical transformation taking place during the solidification. For example, white cast iron shrinks by about 21.0 mm/m during casting. However, it grows by about 10.5 mm/m after being annealed, resulting in a net shrinkage of 10.5 mm/m. Similarly, in gray cast iron and spheroidal graphite iron, the amount of graphitization controls the actual shrinkage. When graphitization is more, the shrinkage would be less and vice versa. The various rates of contraction for the materials are given in Table 3.1. As a rule, all the dimensions are going to be altered uniformly unless they are restrained in some way. For example, a dry sand core at the center of the casting may restrain the casting from contracting, but the edges are not restrained. Thus, it may be desirable to provide a higher shrinkage allowance for outer dimensions compared to ones which may be restrained. The actual value of shrinkage depends on various factors specific to a particular casting, namely the actual composition of the alloy cast, mold materials used, mold design, complexity of the pattern, and the component size. The pattern maker's experience and a little bit of trial are to be used in arriving at the final shrinkages provided on the pattern. The values shown in Table 3.1 are average values and higher values are to be used for smaller dimensions and vice versa. The shrinkage allowance is always to be added to the linear dimensions. Even in case of internal dimensions, e.g. internal diameters of cylinders, the material has a tendency to contract towards the center, and thus are to be increased. It is also possible to obtain shrink rulers for specific materials, such as steels, which are nothing but special scales where dimensions shown are actually longer by a measure equal to the shrinkage allowance. Dimensions provided by such a rule can be used at the time of making the pattern. Different shrink rulers are used for different casting materials. Metal casting processes 3.7. Table 3.1 Shrinkage allowances for various metals. Material pattern dime cyan, section thickness, shrinkage allowance, m/m gray cast iron. White cast iron ductile iron malleable iron. Up to 600 to 1200 over 1200. $1,200. 9, 12, 15, 18, 22, 25. 10.5, 8.5, 7.0, 16.0, to 23.0, 8.3, to 10.4, 11.8, 10.5, 9.2, 7.9, 6.6, 4.0, 2.6. Plain carbon steel. Chromium steel, manganese steel. Up to 600 to 1800 over 1800. $21.0, 16.0, 13.0, 20.0, 25.0, to 38.0. Aluminium bronze. 13.0, 20.0, to 23.0. Copper brass bronze gunmetal manganese bronze silicon bronze tin bronze chromium copper. $16.0, 15.5, 15.5, to 22.0, 10.0, to 16.0, 15.6, 10.4, 10.4, 20.8. Lead, 26.0 Monel, 20.0 magnesium alloys. 13.0, 16.0. White metal, 6.0 zinc, 10.0 to 15.0. Example 3.1. The casting shown in Fig. 3.3a is to be made in plain carbon steel using a wooden pattern. Assuming only shrinkage allowance, calculate the dimensions of the pattern. 3.8 Manufacturing technology, foundry, forming and welding. 080. 100 200. 200. 150 100. 081.7. 102.1 204.2. 153.2. 082.7. 103.4 206.8. 155.1. A. B. C. 080. Fig. 3.3 Provision of allowances for patterns in sand castings, all dimensions in mm. From Table 3.1, for steel the shrinkage allowance is 21.0 mm/m. For dimension 200, allowance is 200 yen. 21.0 divided by 1000 is equal to 4.20 mm. For dimension 150, allowance is 150 yen. 21.0 divided by 1000 is equal to 3.15. 3.20 millimeters. For dimension 100, allowance is 100 yen. 21.0 divided by 1000 is equal to 2.10 mm. For dimension 80, allowance is 80 yen. 21.0 divided by 1000 is equal to 1.68. 1.70 millimeters. The pattern drawing with required dimensions taking shrinkage into account is shown in Fig. 3.3b. Double shrinkage allowance is to be provided on the pattern dimensions, if it is to be used for casting the metallic pattern, which would ultimately be used for molding to take care of the shrinkage of the actual metal cast as well as the shrinkage of the pattern metal. This is illustrated in the following example. Example 3.2. For the same example as shown in Fig. 3.3a, if the master pattern is to be made of aluminium, then calculate the dime cyans of the wooden pattern, which is to be used for making the aluminium pattern. Figure 3.3b shows the dimensions of the aluminium pattern. From Table 3.1, for aluminium the shrinkage allowance is 13.0 mm/m. For plain carbon steel it is 21.0 mm/m. The total shrinkage equals 13.0 plus 21.0 is equal to 34.0 mm/m. For dimension 200, allowance is 200 yen. 34.0 divided by 1000 is equal to 6.80 mm. For dimension 150, allowance is 150 yen. 34.0 divided by 1000 is equal to 5.10 mm. For dimension 100, allowance is 100 yen. 34.0 divided by 1000 is equal to 3.40 mm. For dimension 80, allowance is 80 yen. 34.0 divided by 1000 is equal to 2.72 mm. The final dimensions of the wooden pattern for making the aluminium master pattern are shown in Fig. 3.3c. The pattern allowance applied for this wooden pattern is called double shrinkage allowance. Metal casting processes 3.9. Finish or machining allowance. The finish and accuracy achieved in sand casting are generally poor, and therefore, when the casting is functionally required to be of good surface,
poor, and therefore when the casting is functionally required to be of good surface finish or dimensionally accurate, it is generally achieved by subsequent machining. Also, ferrous materials would have scales on the skin which are to be removed by cleaning. Hence, extra material is to be provided which is to be subsequently removed by machining or cleaning process. This depends on dimensions, the type of casting material and the finish required. This may range from 2 to 20 mm. General guidelines for machining allowances are provided in the table 3.2. The machining allowance provided ultimately has to be removed by machining. Hence, the cost of providing additional machining allowance should be carefully examined before finalizing. The type of machining allowance provided would depend on the metal cast, the type of molding used, the class of accuracy required on the surface, and the complexity of surface details. One way of reducing the machining allowance is to keep entire casting in the drag flask such that dimensional variation and other defects due to the parting plane are reduced to a minimum. Example 3.3. In the previous example 3.2, what will be the pattern dimension if all the surfaces of the casting need to be machined? From table 3.2, machining allowance for bore equals 3 mm. Machining allowance for all surfaces equals 3 mm. Machining allowance for cope side equals 6 mm. The dimension 80, 80 plus 2 yen 3 equals 86 mm. The dimension 100, 100 plus 3 plus 6 equals 109 mm. The dimension 150, 150 plus 3 plus 3 equals 156 mm. The dimension 200, 200 plus 5.5 plus 5.5 equals 211 mm. The final dimensions are shown in Fig 3.4.
Table 3.2 Machining allowances on patterns for sand castings.
Up to 300, 301 to 500, 501 to 900.
.0, 5.0, 6.0. 3.0, 4.0, 5.0. 5.5, 6.0, 6.0 cast steel up to 150, 151 to 500, 501 to 900. 3.0, 6.0, 7.0. 3.0, 5.5, 6.0. 6.0, 7.0, 9.0 non-ferrous up to 200, 201 to 300, 301 to 900. 2.0, 2.5, 3.0. 1.5, 1.5, 2.5. 2.0, 3.0, 3.0. 3.10 Manufacturing technology, foundry, forming and welding. Parting line. Machining allowance. 074. 080. 109. 211. Fig. 3.4 Pattern after providing machining allowance, all dimensions in mm.
Draft. At the time of withdrawing the pattern from the sand mold, the vertical faces of the pattern are in continual contact with the sand, which may damage the mold cavity, as shown in Fig 3.5a. To reduce its chances, the vertical faces of the pattern are always tapered from the parting line, Fig 3.5b. This provision is called draft allowance. Draft allowance varies with the complexity of the job. But in general, inner details of the pattern require higher draft than outer surfaces. Table 3.3 is a general guide to the provision of drafts. The draft allowance given varies for hand molding and machine molding. More draft need to be provided for hand molding compared to machine molding. In machine molding, the actual draft given varies with the condition of the machine, new, rigid, properly aligned, etc., require less draft. An observation here is that draft is always provided as an extra metal over and above the original casting. Dimensions as shown in the following example. Example 3.4.
Provide draft allowance to the pattern shown in Fig. 3. Example 3.4. At the time. Draft. At the time of withdrawing the pattern from the sand mold, the vertical faces of the pattern are in continual contact with the sand, which may damage the mold cavity, as shown in Fig. 3.5a. To reduce its chances, the vertical faces of the pattern are always tapered from the parting line, Fig. 3.5b. This provision is called draft allowance. Draft allowance varies with the complexity of the job. But in general, inner details of the pattern require higher draft than outer surfaces. Table 3.3 is a general guide to the provision of drafts. The draft allowance given varies for hand molding and machine molding. More draft need to be provided for hand molding compared to machine molding. In machine molding, the actual draft given varies with the condition of the machine, new, rigid, properly aligned, etc., require less draft. An observation here is that draft is always provided as an extra metal over and above the original casting. Dimensions as shown in the following example. Example 3.4. Provide draft allowance to the pattern shown in Fig. 3.4 after providing the machining allowance. Allowance. From Table 3.3, the draft angle is 0.75 degrees for external details and 1 degree for internal details. Draft need to be provided only for the dimensions that are perpendicular to the parting line. Hence, for 109 mm size, the taper required is external equals 109 yen tan, 0.75, equals 1.4268 1.40 mm internal equals 109 yen tan, 1.00, equals 1.9026 1.90 mm. Parting line. A. B. Fig. 3.5 effective draft on pattern withdrawing. Table 3.3 suggested draft values for patterns. Pattern material height of the given surface, draft angle of surfaces, degrees. External surface, internal surface. Wood 2021 to 50 51 to 100 100 and 1 to 200 200 and 1 to 300 300 and 1 to 800 800 and 1 to 2000 over 2000. 3.00 1.50 1.000 0.75 0.50 0.50 0.35. Three point zero zero 2.50 1.50 1.00 1.00 0.75 0.50 0.25. Metal and plastic 2021 to 50 51 to 100 100 and 1 to 200 200 and 1 to 300 300 and 1 to 800. 1.50 1.00 0.75 0.50 0.50 0.35. 3.00 2.00 1.00 0.75 0.75 0.50. Parting line. 074. 109. 211. 070.2 213.8. 074 211. A. B. Fig. 3.6 example showing the application of draft, all dimensions in mm. 3.12 Manufacturing technology, foundry, forming and welding. Shake allowance. Before withdrawal from the sand mold, the pattern is wrapped all around the vertical. Before withdrawal from the sand mold, the pattern is wrapped all around the vertical faces to enlarge. Before withdrawal from the 3.12 Manufacturing. Fig. 3.6 example showing the 3.12 Manufacturing technology, foundry, forming and welding. Shake allowance. Before withdrawal from the sand mold, the pattern is wrapped all around the vertical faces to enlarge the mold cavity slightly, which facilitates its removal. Since it enlarges the final casting made, it is desirable that the original pattern diamond science should be reduced to account for this increase. There is no sure way of quantifying this allowance since it is highly dependent on the foundry personnel and practices involved. It is a negative allowance and is to be applied only to those dimensions which are parallel to the parting plane. One way of reducing this allowance is to increase the draft which can be removed during the subsequent machining. Distortion allowance. A metal when has just solidified is very weak and therefore is likely to be distortion prone. This is particularly so for weaker sections such as long flat portions, V/U sections, or in a complicated casting which may have thin and long sections connected to thick sections. The foundry practice should be to make extra material provision for reducing the distortion. Alternatively, the shape of pattern itself should be given a distortion of equal amount in the opposite direction of the likely distortion direction. This can be done by trial and error basis to get the distortion amount. Some data about a few test cases may be available from the literature. Literature. 3.2.2 Core prints. For all those castings where coring is required, provision should be made to support the core inside the mold cavity. One of the methods that are universally followed is to provide core prints where possible. Figure 3.7 shows an example of the provision of core prints. The size of the core prints to be provided is estimated based on the specific casting, the details of which are provided later. Job. Pattern. Mold. Core. Fig. 3.7 Typical job, its pattern and the mold cavity. Metal casting processes 3.13. 3.2.3 Elimination of details. Often it is not possible to get very fine details on the surface or very small small holes by sand casting. In such cases, it is desirable to simplify the casting process by eliminating those details and get them during the finishing process employed. One such example is presented in Fig. 3.8. The types of details that one would like to eliminate in the casting depend on the required accuracy, the capability of the chosen casting process, and the molding method employed. 5885. 3. Cast component. 358080. 87 196 2216. 1.528. 85. 18. 18. 80 86 15. 10 15 26. 710. Pattern materials. The usual pattern materials are wood, metal, and plastics. The most commonly used pattern material is wood, because of its easy availability, low weight, can be easily shaped, and is relatively cheap. But the main disadvantage of wood is its absorption of moisture, as a result of which distortions and dimensional changes occur. A good construction may be able to reduce the warpage to some extent. Hence, proper seasoning and upkeep of wood is almost a prerequisite for large-scale use of wood as a pattern material. The usual varieties of wood commonly used for making patterns are pine, mahogany, teak, walnut, and deodar. Besides the wood, the plywood boards of the veneer type as well as the particle boards are also used for making patterns. Because of their availability in various thicknesses, their higher strength, and no need for seasoning are the reasons for their usage. However, they can be used only in patterns which are of flat type. Pattern plates, and no three-dimensional contours. 3.14 Manufacturing technology, foundry, forming and welding. Welding. Choice of the pattern material depends essentially on the size of the casting, the number of castings to be made from the pattern, and the dimensional accuracy required. For very large castings, wood may be the only practical pattern material. Molding sand being highly abrasive for large-scale production, wood may not be suitable as a pattern material, and one may have to opt for metal patterns. Because of their durability and smooth surface finish, metal patterns are extensively used for large-scale casting production and for closer dimensional tolerances. Though many materials such as cast iron, brass, etc., can be used as pattern materials, aluminium and white metal are most commonly used. These are light, can be easily worked, and are corrosion resistant. Since white metal has very small shrinkage, it can be used for making additional patterns without worrying about the double shrinkage allowances. Most metal patterns are cast in sand molds from a master wood pattern provided with the double shrinkage allowance. Comparative advantages and disadvantages of various pattern materials are shown in Table 3.4. Table 3.4 Comparative characteristics of metallic pattern materials. Pattern metal advantages, disadvantages: aluminium alloys, good machinability, high corrosion resistance, low density, good surface finish. Low strength, high cost. Gray cast iron, good machinability, high strength, low cost. Corrosion prone, high density. Steel, good surface finish, high strength, corrosion prone, high density. Brass and bronze, good surface finish, high strength, high corrosion resistance. High cost, high density. Lead alloys, good machinability, high cost, high density, low strength. Plastics are also used as pattern materials because of their low weight, easier formability, smooth surfaces, and durability. They do not absorb moisture and are therefore dimensionally stable and can be cleaned easily. The making of a plastic pattern can be done in sand clay molds or molds made of plaster of Paris. The most generally used plastics are cold-setting epoxy resins with suitable fillers. With a proper combination, it is possible to obtain no-shrink plastic material. In such a case, double shrinkage allowances may not be required. Polyurethane foam is also used as pattern material. It is very light and can be easily formed into any shape required. It can be used for light-duty work for small number of castings for the conventional casting, and for single casting in the case of full mold process, where the pattern is burned inside the mold without withdrawing. This plastic has very low ash content, and hence can be burned inside the mold. The pattern material is to be chosen based on the expected life of the pattern. Table 3.5 gives comparative values of pattern material choices. 3.2.5 Types of patterns. There are various types of patterns depending upon the complexity of the job, the number of castings required, and the molding procedure adopted. Metal casting processes 3.15. Table 3.5 Pattern materials based on expected life. Number of castings produced before pattern equipment, repair pattern material pattern core small castings, under 600 millimeters. 200060001000. 200060001000. Hardwood aluminium, plastic cast iron. Medium castings, 600 to 1800 millimeters, 100030000753 hardwood aluminium, plastic large castings, above 1800 millimeters, 200 500 150 500 softwood hardwood metal reinforced. Single piece pattern. These are inexpensive and the simplest type of patterns. As the name indicates, they are made of a single piece as shown in Fig. 3.9. This type of pattern is used only in cases where the job is very simple and does not create any withdrawal problems. It is also used for applications in very small scale production or in prototype development. This pattern is expected to be entirely in the drag. One of the surfaces is expected to be flat, which is used as the parting plane. If no such flat surface exists, the molding may become complicated with the necessity of a follow board as explained later. A casting B pattern. Fig. 3.9 single piece pattern. Split pattern or two-piece pattern. This is the most widely used type of pattern for intricate castings. When the contour of the casting makes its withdrawal from the mold difficult, or when the depth of the casting is too high, then the pattern is split into two parts so that one part is in the drag and the other in the cope. The split surface of the pattern is same as the parting plane of the mold. The two halves of the pattern should be aligned properly by making use of the dowel pins, which are fitted to the cope half. These dowel pins match with the precisely made holes in the drag half of the pattern, and thus align the two halves properly as seen in Fig. 3.10. 3.16 Manufacturing technology, foundry, forming and welding. Gated pattern. This is an improvement over the simple pattern, where the gating and runner system are integral with the pattern. This would eliminate the hand cutting of the runners and gates, and will help in improving the productivity of a molder. Cope and drag pattern. These are similar to split patterns. In addition to splitting the pattern, the cope and drag halves of the pattern along with the gating and risering systems are attached separately to the metal or wooden plates along with the alignment pins, Fig. 3.11. They are called the cope and drag patterns. The cope and drag molds may be produced using these patterns separately by two mold ERS, but they can be assembled to form a complete mold. These types of patterns are used for castings, which are heavy and inconvenient for handling, as also for continuous production. A part. B. Cope half of pattern. C. Drag half of pattern. Gating system. Fig. 3.11 Cope and drag pattern. Match plate pattern. These are extensions of the previous type. Here the cope and drag patterns along with the gating and the risering are mounted on a single matching metal or wooden plate on either side as shown in Fig. 3.12. On one side of the match plate the cope flask is prepared and on the other, the drag flask. After molding when the match plate is removed, a complete mold with gating is obtained by joining the cope and the drag together. Dowel pins. Fig. 3.10 Split pattern. Metal casting processes 3.17. Runner. Bushing. Hole. Gate cope side. Lock casting flat plate. Cope. Drag. Cylindrical casting. Drag side. Match plate. Fig. 3.12 Match plate pattern, courtesy J.S. Campbell, Principles of Manufacturing Materials and Processes, P. 153, McGraw-Hill, New York. The complete pattern with match plate is entirely made of metal, usually aluminium for its light weight and machinability. But when dimensions are critical, the match plate may be made of steel with necessary case hardening of the critical aluminium for its light weight and machinability. But when dimensions are critical, the match plate may be made of steel with necessary case hardening of the critical wear points. The pattern and gating are either screwed to the match plate in the case of a flat parting plane, or are made integral in case of an irregular parting plane. The casting of a match plate pattern is done usually in plaster molds, but sometimes sand molds are also used. When the cope and the drag patterns are similar, the pattern may be kept on only one side of the plate, and is used for making both the drag as well as the cope. These are generally used for small castings with higher dimensional accuracy and large production. The gating system is already made and attached to the match plate. Several patterns can be fixed to a single match plate if they are sufficiently small in size. These patterns are used for machine molding. They are expensive. But since they increase productivity, the additional cost is justified. Loose piece pattern. This type of pattern is also used when the contour of the part is such that withdrawing the pattern from the mold is not possible. Hence, during molding, the obstructing part of the contour is held as a loose piece by a wire. After molding is over, first the main pattern is removed, and then the loose pieces are recovered through the gap generated by the main pattern, Fig. 3.13. Molding with loose pieces is a highly skilled job and is generally expensive and therefore should be avoided where possible. Follow board pattern. This type of pattern is adopted for those castings where there are some portions which are structurally weak, and if not suppo-root properly are likely to break under the force of ramming. Hence the bottom board is modified as a follow board to closely fit the contour of the weak pattern, and thus support it during the ramming of the drag. During the preparation of the cope, no follow board is necessary, because the sand. This type of pattern is adopted for those castings where there are some portions which are structurally weak, and if not suppo-root properly are likely to break under the force of ramming. Hence the bottom board is modified as a follow board to closely fit the contour of the weak pattern, and thus support it during the ramming of the drag. During the preparation of the cope, no follow board is necessary, because the sand that is already compacted in the drag will support the fragile pattern. An example is shown in Fig. 3.14. 3.18 Manufacturing Technology, Foundry, Forming and Welding. Loose piece A. Loose piece left in the mold after pattern removal, BPL loose piece. Fig. 3.13 Loose piece pattern. Follow board Fig. 3.14 Follow board pattern. Sweep pattern. It is used to sweep the complete casting by means of a plane sweep. These are used for generating large shapes which are axis, symmetrical, or prismatic in nature, such as bell-shaped or cylindrical as shown in Fig. 3.15. This greatly reduces the cost of a three-dimensional pattern. This type of pattern is particularly suitable for very large castings, such as bells for ornamental purposes used, which are generally cast in pit molds. Spindle well ram sand. ABC. Sweep completed mold. Fig. 3.15 Sweep pattern. Metal casting processes 3.19. Skeleton pattern. A skeleton of the pattern made of strips of wood is used for building the final pattern by packing sand around the skeleton. After packing the sand, the desired form is obtained with the help of a strickle as shown in Fig. 3.16. The type of skeleton to be made is dependent upon the geometry of the workpiece. This type of pattern is useful generally for very large castings required in small quantities, where large expense on complete wooden pattern is not justified. Fig. 3.16 Skeleton pattern. 3.2.6 Pattern color code. The patterns are normally painted with contrasting colors such that the mold maker would be able to understand the functions clearly. The color code used is 1. Red or orange on surfaces, not to be finished and left as cast 2. Yellow on surfaces to be machined 3. Black on core prints for unmachined openings 4. Yellow stripes on black on core prints for machined openings 5. Green on seats of and for loose pieces and loose core prints 6. Diagonal black stripes with clear. The patterns are normally painted with contrasting colors such that the mold maker would be able to understand the functions clearly. The color code used is 1. Red or orange on surfaces, not to be finished and left as cast 2. Yellow on surfaces to be machined 3. Black on core prints for unmachined openings 4. Yellow stripes on black on core prints for machined openings 5. Green on seats of and for loose pieces and loose core prints 6. Diagonal black stripes with clear varnish on to strengthen the weak patterns, or to shorten a casting. 3.2.7 Additive manufacturing, rapid 3.2.7 The patterns are normally painted with contrasting colors such that the mold maker would be able to understand the functions clearly. The color code used is 1. Red or orange on surfaces, not to be finished and left as cast 2. Yellow on surfaces to be machined 3. Black on core prints for unmachined openings 4. Yellow stripes on black on core prints for machined openings 5. Green on seats of and for loose pieces and loose core prints 6. The patterns are normally painted with contrasting colors such that the mold maker would be able to understand the functions clearly. The color code used is 1. Red or orange on surfaces, not to be finished and left as cast 2. Yellow on surfaces to be machined 3. Black on core prints for unmachined openings 4. Yellow stripes on black on core prints for machined openings 5. Green on seats of and for loose pieces and loose core prints 6. Diagonal black stripes with clear varnish on to strengthen the weak patterns, or to shorten a casting. 3.2.7 Additive manufacturing, rapid prototyping. Additive manufacturing, AM, is a process that uses direct digital 3D model data to build physical parts by depositing layer by layer of the build material. It is also more prominently being called 3D printing as a synonym for additive manufacturing. This process is in contrast from traditional material removal processes, where a workpiece is obtained from solid block by removing the unwanted material. The process was first demonstrated in 1987 by 3D Systems, and is originally conceived as a rapid prototyping process to produce prototypes during the product design stage. Since then the process evolved into more prominence by offering its use for making final parts, as well as tooling required for the manufacturing operations. Though the first demonstrated process utilized photopolymer as the build material, now a range of different metals, plastics, and composite materials are available for additive manufacturing. The process starts with developing the part model in a 3D CAD system. The CAD model is then translated into STL, standard tessellation language that was originally adopted by the stereolithography process by 3D Systems, format acceptable for AM machines. CAD model of the part is then sliced using a number of horizontal planes that are parallel to 3.20 Additive manufacturing, AM, is a process that uses direct digital 3D model data to build physical parts by depositing layer by layer of the build material. It is also more prominently being called 3D printing as a synonym for additive manufacturing. This process is in contrast from traditional material removal processes, where a workpiece is obtained from solid block by removing the unwanted material. The process was first demonstrated in 1987 by 3D Systems, and is originally conceived as a rapid prototyping process to produce prototypes during the product design stage. Since then the process evolved into more prominence by offering its use for making final parts, as well as tooling required for the manufacturing operations. Though the first demonstrated process utilized photopolymer as the build material, now a range of different metals, plastics, and composite materials are available for additive manufacturing. The process starts with developing the part model in a 3D CAD system. The CAD model is then translated into STL, standard tessellation language that was originally adopted by the stereolithography process by 3D Systems, format acceptable for AM machines. CAD model of the part is then sliced using a number of 3.20 manufacturing technology, foundry, forming and welding. Horizontal planes that are parallel to each other and separated by a distance equivalent to the resolution of the AM machine, such as 0.125 mm as shown in Fig. 3.17. The AM machine will then add support material, where required to have a bottoms-up build process, and all the layers are supported uniformly. Support object. Support object. A, B, C. Fig. 3.17 Concept of layer manufacturing. A. Shape data as input in the CAD system. B. CAD model is sliced into layers. C. Each of the layer is then deposited starting from the bottom until the model is completed. The machine then starts creating the bottom-most layers. Layers. The system then generates trajectories for the material to be added in each layer by the RP machine. The sacrificial supporting layers are also simultaneously generated to keep the unconnected layers in proper position. The resultant separate cross-sectional layers of very small thickness, when assembled, glued, together will form the final object required. After completing the building process, the model and supports, if any, are removed from the machine, and the surface of the model is then finished and cleaned. As already mentioned, additive manufacturing was originally developed for prototyping. However, in view of its versatility, it has been used in a number of ways in manufacturing. One of the first uses was for developing tooling required for other manufacturing operations, such as patterns for investment casting and permanent molds. It is normally called as rapid tooling as shown in Fig. 3.18. The other way to use AM is rapid manufacturing, where the actual parts required are directly manufactured using AM. Typical examples are the difficult-to-get spare parts and complex parts that cannot be manufactured by normal manufacturing operations. The ASTM Committee F42 on Additive Manufacturing Technologies formed in 2009 looks after the various matters related to AM. The ASTM approved AM process categories, ISO/ASTM 52900-15-R. VAT photopolymerization, an additive manufacturing process, in which liquid photopolymer, in a vat is selectively cured by light, activated polymerization. An example is SLA, stereolithography apparatus. VAT photopolymerization, an additive manufacturing process, in which liquid photopolymer, in a vat is selectively cured by light, activated polymerization. An example is SLA, stereolithography apparatus. Stereolithography was patented in 1986 by Charles W. Hull. Sheet lamination. Lamination, an additive manufacturing process in which sheets of material are bonded to form an object. An example is LOM, laminated object manufacturing that utilized adhesive-backed paper as the build material. Material jetting, an additive manufacturing process in which droplets of build material are selectively deposited. An example is poly-jet that dispenses photopolymer resin through multiple jets that would be solidified by exposure to UV light. Metal casting processes 3.21. Additive manufacturing. Rapid manufacturing, rapid tooling, rapid prototyping. Polymer metal, ceramic, composite, polymer metal. Fig. 3.18 The three branches of additive manufacturing operations. Operations. Powder bed fusion, an additive manufacturing process in which thermal energy selectively fuses regions of a powder bed. An example is SLS, selective laser sintering, where the heat from laser fuses the powder particles to form the layers. Binder jetting, an additive manufacturing process in which a liquid bonding agent is selectively deposited to join powder materials. An example is 3DP, 3D printing, also known as inkjet powder printing, using a technology invented by MIT. Material extrusion, an additive manufacturing process in which material is selectively dispensed through a nozzle or orifice. An example is FDM, fused deposition modeling, where a plastic wire is melted in a nozzle and dispensed to form the solid layer. Directed energy deposition, an additive manufacturing process in which focused thermal energy is used to fuse materials by melting as the material is being deposited. An example is LENS, laser-engineered net shaping pioneered by Sandia National Laboratories. These processes use the build material that is either liquid powder or solid, and can therefore be classified based on the nature of build material as shown in Fig. 3.19. AM processes. Liquid-based, solid-based, powder-based. Slalom SLS EBM LENS FDM 3DP. Sheet lamination material jetting powder bed fusion binder jetting material extrusion directed energy deposition vat photopolymerization. Polyjet. Fig. 3.19 Classification of the additive manufacturing technologies. 3.22 Manufacturing technology, foundry, forming and welding. Stereolithography, SLA. The most commonly used process for rapid prototyping is the stereolithography, or photolithography. These systems build shapes using light to selectively solidify photocurable resins. Stereolithography machines convert three-dimensional CAD data of physical objects into vertical stacks of slices. A low-power ultraviolet laser beam is then carefully traced across a vat of photocurable liquid polymer, producing a single layer of solidified resin, the first slice of the object under construction. The laser beam is guided across the surface by servo-controlled galvanometer mirrors, drawing a cross-sectional pattern in the X-Y plane to form a solid section. The initial layer is then lowered incrementally by the height of the next slice, where the layer is recoated with resin, and another is traced on top of it, Fig. 3.20. This procedure is repeated until the entire part is fabricated. After completing the build process, the part is taken out of the SLA machine and cured as. The UV laser used in the process does not have sufficient strength to completely cure the polymer. Though this was the first process commercialized, it is expensive and is limited to some of the photo-curable plastic materials only. This process is used to make complex master patterns for all casting processes. Sometimes it may also be used for low-volume production of investment casting patterns as well. Scanning mirror laser. Recoating bar liquid resin to form model, cured resin. Platform. Fig. 3.20 Schematic of stereolithography device. Selective laser sintering, SLS. In the selective laser sintering, SLS, process, originally developed at the University of Texas at Austin, a modulated laser beam follows the shape of a slice of a CAD-generated object. It traces the object across a bin of special heat, fusible powders, heating the particles so they fuse or sinter together. In SLS, a layer of powdered material is spread out and leveled in the plane where the layer is to be formed. A CO2 laser then selectively traces the layer to fuse those areas defined by the geometry of the cross-section along with fusing to the bottom layer. The powders can be joined by melting or surface bonding. The unfused material remains in place as the support structure. After the initial layer is formed, powder is reapplied and the laser. Metal casting processes 3.23. Processes the next layer. Some of the materials used are plastics, waxes and low melting, temperature metal alloys. Because of the use of metal powders, this process is greatly used in applications such as direct tool ING applications for investment and die casting applications discussed later. This process is used for making low-volume metallic molds used for permanent mold casting and die casting. It can also make the dies for making the patterns for investment casting. 3D printing, 3DP. 3D printing can be compared to SLS with a difference that instead of laser beam, liquid binder is applied to bond the powder particles. A 3D printer is operated in the following sequence. The printer spreads a layer of powder from the feed box to cover the surface of the build platform, and then prints binder solution onto the loose powder, forming the first cross-section of the part. Where the binder is printed, the powder's particles are glued together. The remaining powder is loose and supports the part as it is being printed. When the cross-section is complete, the build platform is lowered slightly and a new layer of powder is spread over its surface. The process is repeated until the whole model is completed. The build platform is raised and the loose powder is vacuumed away, revealing the completed part. Fused deposition modeling, FDM. In this process a plastic filament is unwound from a coil and supplies material to an extrusion nozzle. The nozzle is heated to melt the plastic and has a mechanism which allows the flow of the melted plastic to be turned on and off. The nozzle is mounted to a mechanical platform which can be moved in both horizontal and vertical directions. As the nozzle is moved over the table in the required geometry, it deposits a thin bead of extruded plastic to form each layer. The plastic hardens immediately after being squirted from the nozzle and bonds to the layer below. Several materials are available for the process including investment, casting wax. Some FDM systems utilize two extrusion nozzles, one for deposition of a build material and second for deposition of washable material to make support environment. Several FDM materials are in the engineering, development stage, including polycarbonate, polypropylene, PMMA, polymethyl methacrylate, and other various polyesters. Laminated object manufacturing, LOM. Laminated object manufacturing, LOM, machine works by actually cutting the slices of the object out of a sheet of paper foil and then bonding them together. The foil comes off the material supply roll, and the laser then cuts around the outline of the layer. It also hatches the foil around the edge so that this can be easily broken away when all of the layers have been bonded together. After the laser has cut out the top layer, a heated roller moves over the top of the foil to bond the layer to the rest of the object. A sensor is used to measure the thickness of the foil as this can vary, and the machine will automatically adjust the dimensions of the layer being cut to account for any variation. The result is a part that looks like laminated wood. A comparison of these technologies is given in Table 3.6. These methods are used for making the patterns and core boxes. Some of the processes are also used for making the metal molds and dies for large volume production. 3.2 For manufacturing technology, foundry, forming and welding. Table 3.6 Summary of some rapid prototyping technologies. System maximum build size, mm, dimensional accuracy, mm. Materials advantages disadvantages. Stereo, lithography, 500 yen. High cost process, support. Selective laser sintering. 550 yen 550 yen 750. Large range of materials, good accuracy, large build size. High cost process, poor surface finish. Fused deposition modeling. 600 yen 5. Support structures needed. Laminated object modeling. 815 yen 560 yen 508, 0.1 to 0.2, paper good accuracy, large build size limited range of materials, support removal necessary, poor material properties. 3.3 Molding materials. A large variety of molding materials are used in foundries for manufacturing molds and cores. They are molding sand, system sand, sand, backing sand, rebonded sand, facing sand, parting sand. Core sand. The choice of molding materials is based on their processing properties. The properties that are generally required in molding materials are refractoriness. It is the ability of the molding material to withstand the high temperatures of the molten metal so that it does not cause fusion. Some refractory materials are given in Table 3.7. Green strength. The molding sand that contains moisture is termed as green sand. The green sand should have enough strength so that the constructed mold retains its shape. Dry strength. When the moisture in the molding sand is completely expelled, it is called dry sand. When molten metal is poured into a mold, the sand around the mold cavity is quickly converted into dry sand as the moisture in the sand immediately evaporates due to the heat in the molten metal. At this stage, it should retain the mold cavity, and at the same time withstand the metallostatic forces. Hot strength. After all the moisture is eliminated, the sand would reach a high temperature when the metal in the mold is still in the liquid state. The strength of the sand that is required to hold the shape of the mold. Hot strength. After all the dry strength. When the moisture. Green strength. The molding sand that contains moisture is termed as green sand. The green sand should have enough strength so that the constructed mold retains its shape. Dry strength. When the moisture in the molding sand is completely expelled, it is called dry sand. When molten metal is poured into a mold, the sand around the mold cavity is quickly converted into dry sand as the moisture in the sand immediately evaporates due to the heat in the molten metal. At this stage, it should retain the mold cavity, and at the same time withstand the metallostatic forces. Hot strength. After all the moisture is eliminated, the sand would reach a high temperature when the metal in the mold is still in the liquid state. The strength of the sand that is required to hold the shape of the mold cavity is called hot strength. Metal casting processes. 3.25. Table 3.7 Properties of some refractory materials. Material melting point, degree C. Coefficient of linear expansion, 106 yen/degree C. Silica, SiO2, 1710-16.2 alumina, Al2O3, 2028.0 magnesia, MgO, 2813.5 thoria, ThO2, 3059.5 zirconia, ZrO2, 2706.5 zircon, ZrO2. SiO2, 2654.5 silicon carbide, SiC, 2703.5 graphite 4200. Permeability. During the solidification of a casting, large amounts of gases are to be expelled from the mold. The gases are those which have been absorbed by the metal in the furnace, air absorbed from the atmosphere, steam, and other gases that are generated by the molding and core sands. If these gases are not allowed to escape from the mold, they would be trapped inside the casting, causing defects. The molding sand should be sufficiently porous so that the gases are allowed to escape from the mold. This gas evolution capability of the molding sand is termed as permeability. Besides these specific properties, the molding sand should also have collapsibility, so that during the contraction of the solidified casting, it does not provide any resistance which may result in cracks in the casting. They should be reusable, and should have good thermal conductive ITY, so that heat from the casting is quickly transferred. 3.3.1 Molding sand composition. The main ingredients of any molding sand are silica grains, SiO2. Clay is binder. Moisture to activate the clay and provide plasticity. Besides, some other materials are also added to these to enhance the specific properties of molding sands, the details of which are given in later chapters. Silica sand. The sand which forms the major portion of the molding sand, up to 96%, is entirely silica grains, the rest being the other oxides such as alumina, sodium, Na2O plus K2O, and magnesium oxide, MgO and Chao. These impurities should be minimized to about 2% since they affect the fusion point of the silica sands. The main source is the river sand, which is used with or without washing. Ideally the silica sand. The sand which forms the major portion of the molding sand, up to 96%, is entirely silica grains, the rest being the other oxides such as alumina, sodium, Na2O plus K2O, and magnesium oxide, MgO and Chao. These impurities should be minimized to about 2% since they affect the fusion point of the silica sands. The main source is the river sand, which is used with or without washing. Ideally the fusion point of sands should be about 1450 degrees Celsius for cast irons, and about 1550 degrees Celsius for steels. In the river sand, all sizes and shapes of grains are mixed. The sand grains may vary in size from a few micrometers to a few millimeters. Shape of the grains may be round, subangular, angular and very angular. The size and shapes of these sand grains greatly affect the properties of the molding sands, which are explained later in this chapter. Zircon sand is basically a zirconium silicate, ZrCO4. The typical composition is ZrO2 equals 66.25%. SiO2 equals 30.96%, Al2O3 equals 1.92%, Fe2O3 equals 0.74%, and traces of other oxides. It is very expensive. In India it is available in Quillan Beach of Kerala. It has a fusion point of about 2400 degrees Celsius, and also a low coefficient of thermal expansion. The other advantages are high thermal conductivity, high chilling power, and high density. It requires a very small amount of binder, about 3%. It is generally used to manufacture precision steel castings requiring better surface finish, and for precision investment casting. 3.26 Manufacturing technology, foundry, forming and welding. Chromite sand is crushed from the chrome, or whose typical composition is Cr2O3 equals 44%, Fe2O3 equals 28%, SiO2 equals 2.5%, Chao equals 0.5%, and Al2O3 plus MgO equals 25%. The fusion point is about 1800 OC. It also requires a very small amount of binder, about 3%. It is also used to manufacture heavy steel castings requiring better surface finish. It is best suited to austenitic manganese steel castings. Olivine sand contains the minerals phosphorite, Mg2CO4, and phyllite, Fe2CO4. It is very versatile sand and the same mixture can be used for a range of steels. Comparative properties relevant for molding of these various base sands are given in table. Given in Olivine sand contains the minerals phosphorite, Mg2. Clays are the most generally used binding agents mixed with the molding sands to provide the strength, because of their low cost and wider utility. The most popular clay types used are kaolinite or fire clay, Al2O32CO22H2O, and bentonite, Al2O34CO2H2O and H2O. Kaolinite has a melting point of 1750 to 1787 degrees Celsius, and bentonite has melting temperature range of 1250 to 1300 degrees Celsius. Of the two, bentonite can absorb more water, which increases its bonding power. The clays besides these basic constituents may also contain some mixtures of lime, alkalis, and other oxides, which tend to reduce their refractoriness. There are basically two types of bentonites, one with sodium as adsorbed ion often called western bentonite, and the other with calcium ion called southern bentonite. Sodium bentonites produce better swelling properties. Volume increases some 10 to 20 times, high dry strength, which lowers the risk of erosion, better tolerance of variations in water content, low green strength, and high resistance to burnout, which reduces clay consumption. In contrast, the calcium bentonites have low dry strength, but higher green strength. It is possible to improve the properties of calcium bentonite by treating it chemically with soda ash, sodium carbonate. The clay chosen for molding sand should give it the requisite strength for the given apply cation, taking into account the metal being cast and thickness of the casting. Normally, the river sand contains a large amount of clay and therefore can be directly used. 3.8 Comparison of foundry-based sand properties. Silica olivine chromite zircon color white, light brown greenish gray black white brown. Hardness 6.0 to 7.0 6.5 to 7.0 5.5 to 7.0 7.0 to 7.5 dry bulk density, LB/FT3, 85 to 100 100 to 125 150 100 Thermal expansion, mm. Apparent heat transfer average low very high. Fusion point, degree C 1427 to 1760 1538 to 1760 1760 to 1982 2038 to 2204 high temperature reaction acid basic acid. Wettability with molten metal easily not generally resistant grain distribution 2 to 5 screens 3 to 4 screens 4 to 5 screens 2 to 3 screens AFS. Metal casting process is 3.27. Water clay is activated by water so that it develops the necessary plasticity and strength. The amount of water used should be properly controlled. This is because a part of the water absorbed by clay helps in bond ing, while the remainder up to a limit helps in improving the plasticity, but more than that it would decrease the strength and formability. The normal percentages of water used are from 2 to 8. Besides these three main ingredients, many other materials also may be added to enhance the specific properties. For example, PLE, cereal binder up to 2% increases the strength. Pitched tined is a by-product in coke making if used in percentages up to 3 would improve the hot strength, and sawdust up to 2% may improve the collapsibility by slowly burning and increase the permeability. There are other materials such as sea coal, asphalt, fuel oil, graphite, molasses, iron oxide, etc., which are also used for obtaining specific properties. Comparative properties of molding sands with various clays are shown in Table 3.9 below. Table 3.9 Comparison of foundry sand properties with various clays. Sodium bentonite fire clay calcium bentonite silica sand, AFS GFN 60, weight percent 95 88 95 clay bond, weight percent 5 12 5 moisture, weight percent 2.5 3.0 2.5 permeability 110 60 108 green compression strength, KPA 76.53 63.43 97.22 dry compression strength, KPA 675.70 468.84 372.32. 3.3.2 Testing sand properties. The molding sand, after it is prepared, should be properly tested to see that the requisite properties are achieved. There are standard tests to be used which are given in relevant Indian standards, and that of other foundry societies, a list of which is given at the end of this chapter. However, a brief review is made here of the general testing methods. Sample preparation. Tests are conducted on a sample of the standard sand. The molding sand should be prepared exactly as is done in the shop on the standard equipment, and then carefully enclosed in a closed container to safeguard its moisture content. Moisture content. As explained earlier, moisture is an important element of the molding sand as it affects many properties. To test the moisture of molding sand, a carefully weighed test sample of 50 g is dried at a temperature of 105 degrees Celsius to 110 degrees Celsius for 2 hours, by which all the moisture in the sand would have been evaporated. The sample is then weighed. The weight difference in grams when multiplied by 2 would give the percentage of moisture contained in the molding sand. Alternatively, a moisture teller can also be used for measuring the moisture content. In this test, the sand is dried by suspending the sample on a fine metallic screen and allowing hot air to flow through the sample. This method of drying completes the removal of moisture in a matter of minutes compared to 2 hours as in the earlier method. Another moisture teller utilizes calcium carbide to measure the moisture content. A measured amount. As explained earlier, moisture content. Explained earlier, moisture is an important element of the molding sand as it affects many properties. To test the moisture of molding sand, a carefully weighed test sample of 50 g is dried at a temperature of 105 degrees Celsius to 110 degrees Celsius for 2 hours, by which all the moisture in the sand would have been evaporated. The sample is then weighed. The weight difference in grams when multiplied by 2 would give the percentage of moisture contained in the molding sand. Alternatively, a moisture teller can also be used for measuring the moisture content. In this test, the sand is dried by suspending the sample on a fine metallic screen and allowing hot air to flow through the sample. This method of drying completes the removal of moisture in a matter of minutes compared to 2 hours as in the earlier method. Another moisture teller utilizes calcium carbide to measure the moisture content. A measured amount of calcium carbide, a little more than actually required for complete reaction, in a container along with a 3.28 Manufacturing technology, foundry, forming and welding. Separate cap consisting of measured quantity of molding sand is kept in the moisture teller. Care has to be taken before closing the apparatus that carbide and sand do not come into contact. The apparatus is then shaken vigorously such that the follow ing reaction takes place. Cap 2 plus 2 H2O AEC2 H2 plus CaOH2. The acetylene, C2H2, coming out will be collected in the space above the sand, raising the pressure. A pressure gauge connected to the apparatus would give directly the amount of acetylene generated, which is proportional to the moisture present. It is possible to calibrate the pressure gauge, or manometer, to directly read the amount of moisture. Clay content. The clay content of molding sand is determined by dissolving or washing it off the sand. To determine the clay percentage, a 50 g sample is dried at 105 to 110 degrees Celsius. The dried sample is taken in a 1-liter glass flask and added with 475 milliliters of distilled water and 25 milliliters of a 1% solution of caustic soda, NaOH 25 g per liter. This sample is then thoroughly stirred. After the stirring for a period of 5 minutes, the sample is diluted with fresh water up to a 150 millimeters graduation mark, and the sample is left undisturbed for 10 minutes to settle. The sand settles at the bottom, and the clay particles washed from the sand would be floating in the water. 125 millimeters of this water is siphoned off the flask, and it is again topped to the same level and allowed to settle for 5 minutes. The above operation is repeated till the water above the sand becomes clear, indicating that all the clay in the molding sand has been removed. Now, the sand is removed from the flask and dried by heating. The difference in weight of the dried sand in 50 g when multiplied by 2 gives the clay percentage in the molding sand. Sand grain size. To find out the sand grain size, a sand sample, which is devoid of moisture, and clay such as the one obtained after the previous testing is to be used. The dried clay-free sand grains are placed on the top sieve of a sieve shaker, which contains a series of sieves one upon the other with gradually decreasing mesh sizes. The mesh sizes are standardized as shown in Table 3.10. The sieves are shaken continuous LY for a period of 15 minutes. After this shaking operation, the sieves are taken apart, and the sand left over on each of the sieve is carefully weighed. Table 3.10 AFS sieve numbers, and their Indian equivalents with sizes. US series equivalent no. ASDM, mesh opening, IS sieve no. Microns multiplying factor. Metal casting processes 3.29. The sand retained on each of the sieve expressed as a percentage of the total mass can be plotted against the sieve number, as in Fig. 3.21 to obtain the grain distribution. But more important is the grain fineness number, GFN, which is a quantitative indication of the grain distribution. To calculate the grain fineness number, each sieve has been given a weightage factor, as shown in Table 3.10. The amount retained on each sieve is multiplied by the respective weightage factor, summed up, and then divided by the total mass of the sample, which gives the grain fineness number. The same can be expressed as GFN equals IAI MFFSS, where me equals multiplying factor for the th sieve phi equals amount of sand retained on the th sieve. 190 80 70 50 40 30 20 10 0. Sieve number. Cumulative. Percentages. 270. Fig. 3.21 sand grain size distribution. A typical example is presented in Table 3.11 for calculating the grain fineness number. This type of sand is normally used in malleable and gray iron foundries for castings, which weigh more than 20 kilograms. By the above definition, the grain fineness number is the average grain size and corresponds to a sieve number through which all the sand grains would pass through, if they were all of the same size. This is a very convenient way of describing the grain size, and its value can be expected between 40 and 220 for the sands used by most of the foundries. Though the sand properties depend on both the grain size and the grain size distribution, GFN is a very convenient way of finding the sand properties since it takes both into AC count. Table 3.12 gives the sieve analysis for the typical sands, which may be used for the purposes mentioned. Permeability, the rate of flow of air passing through a standard specimen under a standard pressure, is termed as permeability number. 3.30 Manufacturing technology, foundry, forming and welding. Sieve number multiplying factor. Sieve number. Percentages. A typical example is 3.30 Manufacturing technology, foundry, forming and welding. Table 3.11 Sieve analysis. Sieve number multiplying factor, me retained sample phi g, retained percentage pi me yen 5 40 32.4955 150 74.85 54. GFN equals 5. GFN equals 2569.85 49. Table 3.12 Typical sand sieve analysis. Sieve number multiplier me sand 1 sand 2 sand 3 sand 4 retained percent pi me pi me sand 1 sand 30 21 20 40. P equals VH. H equals height of the sand, where V equals volume of metal casting process is 3.31, where V equals metal casting. The standard permeability test is to measure time taken by a 2000 cub cm of air at a pressure typically of 980 pascals, 10 G/cm2, to pass through a standard sand specimen confined in a specimen tube, Fig. 3.22. The standard specimen size is 50.8 mm in diameter, and a length of 50.8 mm. Then, the permeability number, P, is obtained by P equals VHPAT. Metal casting process is 3.31.